So last time I introduced the start of rigid body kinetics, and in rigid body kinetics we know these things. We know first that the net external force on a rigid body is equal to the mass of the rigid body times the acceleration of its center of mass. And in fact, that's true for however particles are organized. It's true for a sack of marbles or a blob of pudding or a rigid body. That's pretty cool. Hopefully you sort of noticed the usefulness of that in the I think it was the second to the last homework problem last time, where you just have a bunch of balls floating in space. You apply a force to one of them, and you can calculate the acceleration of the center of mass of all of them based on that. Whether they're bouncing off each other, whether they're not, it's a pretty flexible fact. And then the second, and this is, okay, so this is Newton's second law. I'm going to call that N2L. And then the second one is the net moment about a point A is equal to the moment of inertia about A times the angular acceleration vector. I'm going to call this one the rotational Newton's second law. You can see that every one of these terms is analogous. Moment is like the rotational version of force. Mass moment of inertia about a point is the rotational analog of mass, and then angular acceleration is analogous to translational acceleration. And we have to define these quantities before we can go on. So the first one is center of mass. So here's what we want to get through. We want to define the center of mass and figure out how to calculate the acceleration of the center of mass. We want to define the mass moment of inertia about a point. And I'm going to try to keep saying mass moment of inertia. Most people normally just talk about it as the moment of inertia, but like I said before, there's two crucially important moments of inertia. You represent them both I sub A, and they calculate two totally different things. So remember the mass on this one. And then the last thing we have to define is the moment. And that one you've done before, but I'll just remind you. So center of mass. I'll abbreviate that COM. The definition of the center of mass is that the position vector of the center of mass is equal to 1 over the total mass times the integral over the entire mass. I guess let's write that as a capital M, of the position vector times the infinitesimal increment of mass. For homogeneous materials, so that's a material, that's an object that's all the same material all the way through. There's no differences as you move from point to point. The position of the center of mass is equal to the centroid. And so when you took statics, those of you who took statics, you probably calculated centroids. The centroid calculation in 2D looks like this. X bar, Y bar is equal to 1 over the total area times the integral over the total area of the centroid of whatever your infinitesimal unit of area is times that infinitesimal area. And you can see the similarity. If you have a homogeneous material, it makes sense that this would be the case because the mass is spread evenly depending on how much material you have. In 2D, that would be area. In 3D, it would be volume. So this is X, Y, Z is equal to 1 over A total, no, B total, times the integral over the full volume of the centroid of your infinitesimal volume times the infinitesimal volume. So as long as it's a homogeneous material, which is usually what we're going to be dealing with, you can use these formulas. But actually, you don't have to use these formulas. We're going to, you don't have to use the integral definition. We're going to use formulas for these. That'll be a lot easier to calculate. Okay, so that gives this integral definition gives the position of the center of mass. In rigid body kinetics, what we need is the acceleration of the center of mass. So how do we calculate the okay, so we need the acceleration of the center of mass. Well, these are integrals with respect to volume. Time doesn't have anything to do with it. So you can just take the time derivatives of both sides of this equation and so take the derivative with respect to time of each side of the equation, and you can come up with the expression for the velocity of the center of mass, which is equal to this should be mass. Let me start over. Velocity of the center of mass is equal to 1 over the total mass times the integral over the total mass times the velocity vector of the center of mass, dm, and the acceleration of the center of mass is equal to 1 over the total mass times the integral of the acceleration of each individual center of mass, dm. Okay, so there's the integral definitions of velocity and acceleration. We won't use this definition, but you can use this definition to come up with formulas for simple shapes or complicated shapes. We're going to use simple ones. So here's what we're really going to use. So the formulas for the centroids of simple shapes. for a semicircle, and actually let's do this as a quarter circle. So there's the centroid location. And I'll call this X bar and this Y bar. These two are both the same, and they're equal to 4 radius of the circle over 3 pi. And then, of course, the area of that shape is equal to pi r squared over 4. And then a right triangle. So let's say this distance is B, and this is H. And the centroid is here. Then this distance is B over 3, and this distance is B over 3. I guess I'll write this as, so call that X bar, call that Y bar. And X bar is equal to B over 3. Y bar is equal to H over 3. And the area of that shape is equal to base times height over 2. Other shapes. There's a sheet that's on D2L, a PDF. I think it's in the section called Course Materials or Course Information in D2L, and it'll list out a whole bunch of ones, parabolas and whatever. But really the other ones that are going to be important for us are rectangular shapes and circles. And you don't have to remember anything about these because of this fact. The centroid always lies on any of any line of symmetry. That's when you're talking about 2D, and these are all 2D shapes. For example, if this is your object, okay, you don't know where vertically the centroid lies, but you do know that it lies somewhere along that dotted line because that's a line of symmetry. And if you have a shape where you can find 2 lines of symmetry, then wherever they intersect, that has to be the centroid. So the centroid is at the intersection. So for example, if you have a rectangular shape, that's a line of symmetry, that's a line of symmetry, so the centroid has to be there. If you have a circle, you can find infinitely many. That picture isn't very convincing, but I think you can believe me there. You know, all the lines of symmetry, there's infinitely many, but they all cross at the center, and so that's the centroid. And let me say, in 3D, it's not lines of symmetry that matter, it's planes of symmetry. And to fully define where the centroid is using symmetry, in 3D you have to find where 3 planes intersect. So the centroid is on any plane of symmetry. And if you have 3 planes of symmetry, the centroid is at the intersection. Now, if you have your object, if your object can be broken up into a collection of these simple shapes, then the centroid follows this formula. So it's basically just a finite version of that integral definition. In 2D, you have that the xy centroid is equal to 1 over the total area times the sum. So say that you have n of these bodies of the centroid of the ith body times, that shouldn't be dA, that should be times the finite area of the ith body. And in 3D, it's the same thing but volume, so 1 over the total volume times the sum from 1 to n of xi, yi, zi bar times vi. Okay, so let me show you how this works. So let's say that we have a shape like this. Let's try to make that. Okay, so those are the same thickness. Let's say that thickness is 0.1 meters. Let's say that this height is 1 meter, and this width is 1 meter. What's the centroid? I'm going to break it up into this rectangle and this rectangle. We know from symmetry considerations that the centroid has to lie somewhere along that line. Using that fact would be a little complicated in this case unless we chose a rotated coordinate system. Let's just put a coordinate system here, and we'll just calculate the x and y components independently. Okay, so I'm going to call this rectangle 1, this rectangle 2. Okay, so what's the area of rectangle 1? Have you guys taken classes where you did areas? Okay, that's so that's a length times a width is how you do rectangles. So 1 times 0.1, so this is 0.1. And then the centroid of that rectangle, because of symmetry, the rectangle centroid is right in the middle. So x is going to be 0.05. And y is going to be 0.5. Okay, see that? And then for the second one, we don't want to overlap materials, so this one has a width of 0.1, a thickness of 0.1, but it's not a full meter long, it's only 0.9 meters long. So A2 is 0.9, no, 0.09. That's what I get for being a smartass. And then x2, y2 is, so what's the centroid of that? It's the whole thing is 0.9, so it's 0.45 meters from its left end, but that's also 0.1 from where the origin is horizontally, right? It's 0.1 to get here, and then another 0.45 to get there. So the x centroid is 0.55. And the y centroid is, you have to go up 0.9 to get to the bottom, and then another 0.05 to get here. So 0.95. The total area is this plus this, so 0.19. And so to find the total centroid, that's equal to 1 over 0.19 times the sum of 0.1 times this vector plus 0.09 times this vector. Can someone punch that in? .0545 and what? 1355. Point.
Oh, sorry.
Okay.
That's the one over there.
Oh, okay. So,
So I got for the X bar 0.287
okay,
and 0.713.
okay, yep, okay. So that makes sense. We'd expect it to be higher than it is far out in the x direction because you have most of your mass centered close to the origin horizontally, and most of it concentrated close to 1 vertically. And we'd have to do some fiddling to figure out if it's on that line, but if we did the calculation right, it has to be. Any questions about that calculation? You can also use that with subtraction. So if you have like a rectangle with a circular shape removed from it, you can take the rectangular shape, A1, times its centroid, minus the area of the removed shape times its centroid, divided by the total area, which is the area of the big thing minus the area of the small thing, and it'll work out that way too. So subtraction works too. So other important facts about this sum approach. Come again from taking d dt of both sides of that equation. And so the velocity of the center of mass is equal to 1 over the total mass times the sum of the individual masses times the individual velocities of the center of mass. And if you're using the centroid, which is usually exactly the same thing, that holds too. So the velocity bar is equal to 1 over the total area times the sum of the individual area of the individual piece times the velocity of the centroid for that individual piece. And what if we take one more time derivative? You think everything goes crazy? Like you get accelerations everywhere? And no, it's pretty predictable. So acceleration of the center of mass is equal to 1 over the total mass times the sum of the ith mass times the acceleration of the center of mass of the ith body. And that also works for centroids. These are in 2D. The 3D one works this way too. Any questions about this? Oh, one kind of interesting thing about this calculation we did is that notice that the center of mass of this object, if you look at those numbers, it's somewhere away from the material. That center of mass doesn't have to lie on a material point. And it makes sense if you think of the center of mass of like a ring or something. You know, the center of mass due to symmetry has to be right in the center, and there's no material there. You know, high jumpers do the thing, the big back arch to get over the bar. If you track the center of mass of a good high jumper, like going over something close to the highest they can go, their center of mass actually entirely goes underneath the bar, and yet every part of their body goes over it. Their body just keeps moving so that their center of mass just drifts a couple inches under, and no part of their body even hits the bar. It's kind of cool. What?
Do you have a video of that?
I'll look for one. I'm sure there's videos on YouTube of that. If you watch an exceptionally bad high jumper, their center of mass goes over the bar, and yet they knock the bar off. I don't know if they take videos of that, though.
There's videos of Eddie the Eagle.
Yeah, that's funny you say that. Did you see there's a movie coming out of Eddie the Eagle? I can't wait for that. Okay, so the next thing we have to define is the mass moment of inertia about a point. So I said you should remember to say mass to yourself when you talk about the moment of inertia. I would even go a step further and, like when somebody else says moment of inertia to you, I'd just be really like condescending about it. Like, do you even know what moment of inertia you're talking about? Do you ever think before you talk, like that kind of stuff? You know, that's the way to get a good reputation in your later engineering departments. Okay? Especially if you do it to professors. People will be like, wow, I'm taking note of this kid. He's going somewhere.
Or just get you F's on your test.
Yeah, probably a little of both, yeah. Okay, so mass moment of inertia. About a point. So if you look at those, at Newton's laws, this sits in the analogous position to mass for the translational one. And so it works a lot similarly to how mass works with translational motion. You know, so just like mass is a measure of resistance to translational acceleration, mass moment of inertia about a point, that's catchy, is a measure of resistance to rotational acceleration, angular acceleration. So, like, this is a real, like, Olympic sport-focused discussion today. Okay, so here's, like, a diver or a gymnast. But, okay, so you get a lot of points for doing your flips like this, and not as many points for doing your flips like this, you know. And the reason is that this has a high mass moment of inertia, and this has a low mass moment of inertia. So it's relatively easy to get this rotating. It's relatively hard to get this rotating, which means you have to spend a lot more time in the air to do the same number of flips, you know. And mathematically, what it depends on is it depends on how far the mass is distributed from the about point, that A that we're calculating this about. If you have more mass farther away from the about point, then you have a high mass moment of inertia. If you have most of the mass concentrated close to the about point, then you have a low mass moment of inertia. In this case, if you were doing dynamics on this, well, so I said that for the rotational version in Newton's second law, you get two choices of about point. The center of mass always works. And then if the object has a point fixed in your coordinate system, then that'll work too. In this case, nothing's fixed in the coordinate system. The guy's just flying through space. So your about point is the center of mass. Their center of mass is in their chest somewhere. So you can see how much more mass of the body is distributed far away from the center of mass here than it is in that position. Okay, so that's what moment of inertia does. Here's the integral definition, and again, we're not going to use that, but you could use that. So the mass moment of inertia about A is equal to the integral over the entire body of r squared dm, where this r is the distance that dm lies from the about point A. The SI units for mass moment of inertia about a point are kilogram meter squared. So instead of using that integral definition, again, I'm going to give you, and I think it's probably already a PDF in D2L, similar to the centroid thing, I'm going to give you a bunch of formulas for simple shapes. And the key thing is to keep in mind is that you can add or subtract moments of inertia, to add or subtract material to build up a more complicated shape. As long as A is the same for both of the bodies. Okay, so is this going to cause problems? Because I'm going to give you moments of inertia formulas for, a handful of simple shapes. But there's infinitely many possibilities for the about point, depending on what the built-up body's center of mass is, if you're using the center of mass, or based on where the body is fixed to the ground, if you're using that as the about point. So I can't give you formulas for every about point. And we have to use the same about point to add up these shapes. Okay? So this is a potential issue. It turns out there's an easy fix for that called the parallel axis theorem. But this is going to be sort of a key thing for using these formulas. So no, but you do have to be careful. Okay, so here are the 4 simple shapes that we're going to use. Moment of inertia for 4. How come I only see 3 shapes there? Oh yeah, 4 simple shapes. Okay, so the first one is a slender rod. The cross-section shape can be anything. It can be, I have it drawn as circular, but it can be rectangular, triangular, whatever. It doesn't matter. And I have to give you the moments of inertia about a bunch of different axes because this can rotate a bunch of different ways. So I'll call that the x-axis. I'll call this the y-axis. And I'll call this the z-axis. Okay. The moment of inertia about y and z is 1/12 times the mass of the object times the length squared. And since we're neglecting the thickness of this, there's no moment of inertia about the x-axis. So that shape doesn't resist angular acceleration about the x-axis at all, but it does about the y or z-axis. Okay, so what? Yes, that's right. So A is right at the origin there. Okay, so the more massive this thing is, or the longer this thing is, the more it resists angular acceleration. The more torque you have to apply to it to cause an angular acceleration. The next one is a thin rectangular plate. So the x-axis is that way. The y-axis is that way. The z-axis is straight out of the front. And so the about point is right in the center. So if this distance is C, and this distance is B, the moment of inertia about the x-axis is 1/12 times the mass times b squared plus c squared. About the y-axis is 1/12 mass times c squared. And about the z-axis is 1/12 mass times b squared. So you have to think about in determining which of these formulas to use, you have to think, is it rotating like I don't know, a thrown knife? Don't throw knives. Or like a paddle on like a paddle wheel boat, you know. If it's rotating like a paddle, then you use the IY or IZ formula. If it's rotating like a blade being thrown through the air, then you use the IX formula. And notice that these reduce to the slender rod formula as like the as that thickness B drops down to 0. So those agree with each other in some sense. Any questions about that? Yep.
When does it stop being a thin or slender?
It just, yeah, that's a good question. I don't have a rule of thumb for that, but it would be easy to punch in some numbers and see how quickly it drops down to 0. It's squared, so it drops down quickly, more quickly than if those were linear. But other than that, it just depends on what level of accuracy you need. Okay, so those are the first two. I'll start with the last two next time.